Okay, in this lesson we're going to learn how to find the sum of an infinite geometric series. In the previous lesson we looked only at finite geometric series that have, a starting term and a specific ending term. But today we're going to look at how can we find the sum of an infinite geometric series. That in some ways sounds kind of strange, actually. Let's just look at the formula again for the geometric series. So we had the sum of the first n terms of a geometric series is the first term times 1 minus r to the nth power over 1 minus r. So suppose r in this case is 1/2. And suppose, in this case, let me plug that into the equation. Sn, the sum of n terms, is the first term times 1 minus r to the n minus, or divided by 1 minus r. Now let's kind of think about, if I have 4 terms, if I'm adding S4, the first 4 terms, then this term right in here is going to be 1/2 to the 4th power, and that's going to be evaluated to 1 over 16. But now if I consider, say, I'm adding 10 terms together, so S10, I will have this 1/2 to the 10th power. Now this becomes 1 over 1024. Let's suppose I'm adding 20 terms together. S20, this will be 1/2 to the 20th power. Now I have 1 over 1 million practically. This number is getting smaller and smaller and smaller. 1/16 isn't too big, or is a decent size, but wow, as you get down to here, this is almost 0, practically 0. And that's the big idea. As n gets bigger and bigger, and 20 is not really a big number. We're talking, say 1,000. 1 over 2 to the 1,000th power would be really, for all practical measures, 0. So if I were to rewrite it like this, so the sum of all the terms from 1 all the way forever and ever, and never stopping, of this infinite series or geometric series A1 1/2 to the n minus 1. In this case, I plug it into my formula. I have 1/2, and I'm going to take liberties and write it like this: 1/2 to the power of infinity. This basically is 0. And so we have 1 minus 0, so then we have a divided by 1/2, which is equal to, if I take the reciprocal of this, 2 times a. So this infinite series actually has a value. It's twice the initial term. Now we can generalize this to any infinite or any sort of infinite series when specifically the value of r is less than 1. And this is a very key concept right here. K or r has to be less than 1, the absolute value. Otherwise it does not, it gets bigger and bigger. Let's look at this. When r is very small, or when r is less than 0, or sorry, when r is less than 1, if I take r to the power of a very big number, basically it goes to 0. As n goes to infinity, r to the power of n goes to 0. And so we can remove all of this from the equation, and it simplifies into a1 over 1 minus r. And this is a kind of nice idea. So suppose I have this series, 5 times 0.8 to the n minus 1 power. It's a geometric series, right? We see this common ratio. R is equal to 0.8. And in fact, let's check to make sure the conditions work out. The absolute value of r is indeed less than 1, so this is a formula we can use for this infinite series where we're adding up an infinite amount of terms. So we use our formula, the first term divided by 1 minus r, 5 divided by 1 minus 0.8, where that's the value of r. 5 divided by 0.2 is 25. So what it's saying is if I took 5 plus 5 times 0.8, which is actually equal to 4, and then I took that value, 5 plus 0.8 times 0.8, and that's equal to, by the way, 3.2, and I kept on doing that forever and ever and ever, it would add up to this very precise number of 25. It doesn't ever get bigger than 25. It's equal to 25. Okay, so try out these next few problems. I'll give you a hint. They might not all be possible. Again, we need to check, is r less than 1? The absolute value of r less than 1. If it's not, we cannot apply this. In that case, the geometric series gets bigger and bigger and bigger. For example, say, let's look at this case here. The sum of I is equal to 1 to infinity of 3 times 2 to the n minus 1. In this case, we see that the value of r is 2, which is greater than 1. In this case, it goes to infinity, and when we cannot use this formula, this will get bigger and bigger and bigger, and there won't be a number like 25 as our answer. The answer to this is really, this goes to infinity. We do not get a single number for it. Okay, so try out these problems. That's the lesson for today.